Introduction to Hypothesis Testing. This is from the ninth chapter of the book, Business Statistics, a Decision-Making Approach, 8th edition. As a business decision maker, you will encounter many applications that will require you to estimate a population parameter. In the last video, a statistical estimation was introduced, and estimating a population parameter based on a sample is a component of business statistics called statistical inference. An important component of statistical inference is hypothesis testing. In hypothesis testing, a hypothesis or a statement concerning a population parameter is identified that we will certify to be true only if the sample evidence is sufficient. We then use sample data to either deny or confirm the validity of the proposed hypothesis. Hypothesis testing is a major part of business statistics, and this chapter introduces the fundamentals involved in conducting hypothesis tests. After completing this chapter, you should be able to formulate null and alternative hypotheses for applications involving a single population mean or proportion, formulate a decision rule for testing a hypothesis, know how to use the test statistic, critical value, and p-value approaches to test the null hypothesis, and know what type 1 and type 2 errors are. Let's begin by defining what a hypothesis is. A hypothesis, simply speaking, is a claim or assumption about a population parameter. A hypothesis can refer to either a population mean or a population proportion. An example of a population mean hypothesis is when we say that the mean monthly cell phone bill of the city is more than 200 pesos. While an example of a population proportion hypothesis would be the proportion of adults in the city with cell phones is at most 68%. By now, you should know that the information contained in a sample is subject to sampling error. The sample mean will almost certainly not equal the population mean. Therefore, in situations in which you need to test a claim about a population by using the sample mean, you can't simply compare the sample mean to the claim and reject the claim if they are different. Instead, we need a testing procedure that incorporates the potential for sampling error. Statistical hypothesis testing provides us with a structured analytical method for making decisions of this type. It helps make decisions in such a way that the probability of decision errors can be controlled or at least measured. In hypothesis testing, two hypotheses are formulated. One is the null hypothesis. The null hypothesis is represented by HO and is the statement about the parameter to be tested. It should contain an equality sign, such as the equal sign, the greater than or equal sign, or the less than or equal sign. The second one is the alternative hypothesis, represented by HA. It challenges the null hypothesis and includes all parameters that are not covered by the null hypothesis. Based on the sample data, we either reject or not reject the null hypothesis. Correctly specifying the null and alternative hypothesis is important because if done incorrectly, the results obtained from this hypothesis test may be misleading. Unfortunately, how you should formulate the null and alternative hypothesis is not always obvious. As you gain experience with hypothesis testing applications, the process becomes easier. Testing the status quo. In many cases, you will be interested in whether a situation has changed. We refer to this as testing the status quo. and this is a common application of hypothesis testing. For example, the Kellogg Company makes many food products, including a variety of breakfast cereals. At the company, frosted mini wheats are produced and packed for distribution around the world. If the packaging process is working properly, the mean fill per box is 16 ounces. Every hour, quality analysts at the plant select a random sample of filled boxes and measure their contents. They do not wish to unnecessarily stop the packaging process, since doing so can be quite costly. Thus, the packaging process will not be stopped unless there is sufficient evidence that the average fill is different from 16 ounces. From the problem, we can formulate the null hypothesis to be equal to 16 ounces because this is the status quo. For the alternative hypothesis, it is when the fill per box is not equal to 16 ounces. The null hypothesis, where the mean fill per box is 16 ounces, is reasonable because the line supervisor would assume the process is operating correctly before starting production. As long as the sample mean is reasonably close to 16 ounces, the analyst will assume the filling process is working properly. Only when the sample mean is seen to be too large or too small will the analyst reject the null hypothesis or the status quo and take action to identify and fix the problem. Testing a research hypothesis. Many business and scientific applications involve research applications. For example, companies such as Intel, Procter & Gamble, Dell Computers, and 3M continually introduce new and hopefully improved products. However, before introducing a new product, the companies want to determine whether the new product is superior to the original. Because statistical evidence is needed to indicate that the new product is effective, the default position or null hypothesis is that it is no better than the original. The burden of proof is placed on the new product, and the alternative hypothesis is formulated as the research hypothesis. For example, suppose the Goodyear Tire and Rubber Company has a new tread design that its engineers claim will outlast its competitor's leading tire. New technology is able to produce tires whose longevity is better than the competitor's tires but are less expensive. Thus, if Goodyear can be sure that the new thread design will last longer than the competition's, it will realize a profit that will justify the introduction of the tire with the new thread design. The competitor's tire has been demonstrated to provide an average of 60,000 miles of use. Therefore, the research hypothesis for Goodyear is that its tire will last longer than its competitors, meaning that the tire will last an average of more than 60,000 miles. The research hypothesis becomes the alternative hypothesis. The burden of proof is on the Goodyear company. Only if the sample data show a sample mean that is substantially larger than the 60,000 miles will the null hypothesis be rejected and the Goodyear's position be affirmed. Testing a claim about the population. Analyzing claims using hypothesis tests can be complicated. Sometimes you will want to give the benefit of a doubt to the claim, but in other instances you will be skeptical about the claim and will want to place the burden of proof on the claim. For consistency purposes, the rule adopted in this text is that if the claim contains the equality sign, the claim becomes the null hypothesis. And if the claim does not contain the equality sign, the claim is the alternative hypothesis. In cases like this, where the claim corresponds to the alternative hypothesis, the burden of proof is on the medical clinic. If the sample mean is substantially less than 15 minutes, the null hypothesis would be rejected and the alternative hypothesis, which is the claim, would be accepted. The hypothesis testing process. After defining the hypothesis from the population, such as the claim that the population mean age is 50 for the null hypothesis, we then select a sample from the population to determine their average age. We then check the likelihood of the sample mean versus the population mean, and if it is not likely, we then reject the null hypothesis and give way for the alternative hypothesis. It is important to take note, though, that the hypothesis we are making refers to the population parameters as a whole and not on the sample parameter. Because of the potential of extreme sampling error, two possible errors can occur when a hypothesis is tested: the type 1 error and the type 2 error. These errors show the relationship between what actually exists and the decision made based on the sample information. Figure 9.1 shows the possible actions and states of nature associated with any hypothesis testing application. As you can see, there are three possible outcomes: no error, or the correct decision has been made, the type 1 error, and the type 2 error. Only one of these will be the outcome for a hypothesis test. And from the figure, if the null hypothesis is true and an error is made, it must be a type 1 error. On the other hand, if the null hypothesis is really false and an error is made, it must be a type 2 error. To illustrate this, let us look at this scenario. The Morgan Lane Real Estate Company has offices in and around the Napa Valley in the Northern California wine country. Before the financial crisis hit the real estate market in late 2008, the market for homes in the Napa Valley area had been hot for a number of years, and homes were commonly sold above the asking price very quickly. The standard time for closings in the Napa was not more than 25 days. The managing partner at Morgan Lane wishes to test whether the mean closing times have changed following the financial crisis. Treating the average closing time of 25 days or less as the status quo, the null and alternative hypotheses to be tested are the following. To test this hypothesis, the managing partner will select a random sample of home sales in the Napa Valley during 2009. In this application, a type 1 error would occur if the sample data led the manager to conclude that the mean closing time exceeds 25 days, when in fact the population mean is less than or equal to 25 days. If a type 1 error occurred, the manager would take no action to improve the closing times at Morgan Lane when in fact changes are needed to improve the customer service. Alternatively, a type 2 error would occur if the sample evidence leads the manager to incorrectly conclude that the population mean is less than or equal to 25 days, when in fact the mean closing time exceeds 25 days. Now, in the type 2 error, the manager would needlessly spend time and resources trying to speed up the process that already meets the original time frame. Comparing type 1 and type 2 errors, type 1 errors is considered to be more serious than type 2 errors. In the Morgan-Lane example, the null and alternative hypotheses were formulated as this. Values of less than or equal to 25 days would tend to support the null hypothesis, and by contrast, values greater than 25 days would tend to refute the null hypothesis. The larger the value of the sample mean, the greater the evidence that the null hypothesis should be rejected. However, because we expect some sampling error, do we want to reject HO for any value that is greater than 25 days? Probably not. But should we reject HO if the sample mean is 26 days, or 27 days, or 30 days? The question is, at what point do we stop attributing the result to sampling error? To perform the hypothesis test, we need to select a cut-off point that is the demarcation between rejecting and not rejecting the null hypothesis. Our decision rule for the Morgan-Lane application would then look like this. This figure shows the assumed position of the cut-off point, or the critical value. If the sample mean is greater than the cut-off value, we will reject HO and conclude that the average closing time does not exceed 25 days. If, however, the sample mean is less than or equal to the cut-off point, we will not reject HO. In this case, our test does not give sufficient evidence that the closing time exceeds 25 days. The figure also shows the distribution for the sample mean assuming that the population mean is 25. The shaded region on the right is called the rejection region. The area of the rejection region gives the probability of getting a sample mean larger than the cutoff. So, it is also the probability of making a type 1 statistical error. This probability is called the significance level of the test and is denoted by the symbol alpha. Simply speaking, the significance level is the maximum allowable probability of committing a type 1 statistical error. Typical values of alpha are 0.01, 0.05, or 0.1. It is selected by the researcher at the beginning of the inference and provides the critical values of the test. Here is the updated figure showing the possible hypothesis test outcomes. If the alpha is the probability of making a type 1 error, the symbol beta is used to denote the probability of making a type 2 error. The two error probabilities, alpha and beta, are inversely related. That is, if we reduce alpha, then beta will increase. Thus, in setting the alpha, you must consider both sides of the issue. Additionally, when all else are equal, beta is high when alpha is low. Beta is high when the population standard deviation is also high. And beta is high when the sample size is low.